All right, Math 5130. Switching gears from ANOVA into chi-squared. Let me explain from kind of a pedagogical perspective why I decided to do this. The most natural statistical technique for me to cover after ANOVA would be two-way ANOVA. But two-way ANOVA is pretty challenging. And I didn't want to end lesson 4, the lesson that comes before your midterm exam, on a real challenging technique. So I'm throwing chi-square, test of independence, and maybe goodness of fit. I haven't decided yet whether I'm going to cover that in this class. But I'm throwing it in after ANOVA, kind of out of sequence, if you will, because I think it's one of the easier things that we cover in this class. So just a little insight on why I'm doing what I'm doing. Chi-square test of independence is what we're going to be studying. What I want you to know about this is when we examine the relationship between two categorical variables, then we use a test of independence, chi-square. If we have a categorical variable and a quantitative variable, then chi-square is not for us. If we have two quantitative variables, chi-square test of independence is not for us. It only applies when we have two categorical variables and we're interested in the relationship between the two. The example that I'm going to use, I got it out of a medical journal. One of the variables is vaccination status, either yes or no. And the other variable is pneumonia. I call this sick. Did the person get sick with pneumonia? Either they did or they did not. So each of these cell counts are interpreted pretty obvious way. 61 people did not get the vaccination and they did not get sick. 77 got the vaccination, they did not get sick. 31 did not get the vaccination, but they got sick. 45 got the vaccination and they got sick. This is our sample data. You can see that I have created the sample data from the vaccination data set. And you can see that the table values match exactly what I have written here. The data that we get from our sample data is called our observed matrix. In calculating our chi-square test statistic, we need to create what's called an expected matrix. I'm going to run through the calculations very quickly just to show you this is not some poof mathematics. Here it is. You know, it just comes from nowhere. You know, if we want the expected matrix, then we're going to use R or StatCrunch to create that, and I'll demonstrate that later. So it's interesting to get the expected matrix. The expected matrix is found by taking for each cell the row total times the column total divided by the total sample size. So if I want the expected matrix for the, if I want the expected cell count for the 61, notice that this 61 is in row 1, row 1, column 1, total sample size 214. So if I want to find the expected cell count for this observed value of 61, I take the row total, 138, times the column total, 92, divided by 214 to get 59.33. Since that cell is in the upper left-hand part, that's where the expected count goes. If I want the bottom right, so the corresponding expected cell count for 45, we take the row total of 76 times the column total of 122, divided by 214 to get 43.33. The test statistic, chi-square test statistic, is found by summing up these values divided by the expected cell count. So the first cell would be the observed value, 61, minus the expected value, 59.33. Square that and divide by 59.33 because that's the expected value. I made these calculations over here. just in case you're interested. I think you have, this is the upper left hand. I think this is the upper right hand. This is the lower left hand. This is the lower right hand. So I squared all that. These are the values that I get. Sum those up. It comes to 2.231. Rounding, got me off just a little bit at 0.233. The p-value, it turns out, is in the chi-square distribution, it's the area to the right of our test statistic. And the chi-square distribution kind of reminds you of the F distribution, but it only has a degree of freedom of one number. For the chi-square test of independence, the degree of freedom is the total number of rows minus 1 times the total number of columns minus 1. We have 2 rows, we have 2 columns, 1 times 1 is 1. So if I can use R to find that area to the right, which I did right here, I'm just demonstrating this. I will never ever ask you to find a p-value this way. If I ask you to find a p-value, I'll ask you to do it using technology. I mean using the R command or StatCrunch command for the chi-square test of independence. So for this, we get that the chi-square degrees of freedom 1, the test statistic is 0.233, p-value 0.629. Now you'll notice over here that I ran the simplified version in R using the chi-square.test for the table. This command only works when you create a table of the 2 categorical variables that you have that you're examining the relationship of. But as a default, it's correct when you have a 2x2 table to do what's called a Yates continuity correction. Now that doesn't actually measure up. It doesn't align with what we got over here, but this is what you would want to report if you were running a 2x2 table. Now, if you add this command, correct equal false, so we're running a 2x2, but we're not running the Yates continuity correction, which we should do again with a 2x2 table. You'll see that the calculations of the straightforward chi-square test gives us the same chi-square statistic, and it gives us the same the p-value. All right. Now,